Good morning, Logan. Welcome to another installment of Geometry at Your Couch. Today we're going to jump into the topic of circles. So the first question that you should be asking yourself is, or I'm going to be asking you, is what is a circle? Yeah, I know what you're looking at on that screen looks like a circle, but the definition of a circle is not just some round object. It's actually a little bit more elegant or more exact, I should say, exact than that. So our definition of circle is going to be this. It's going to be a bunch of points. I know it sounds super high tech, a bunch of points. It's going to be a bunch of points that are all equidistant to a common point. All right, and you're like, okay, so what exactly are you talking about here? Well, what if I was taking a look at this circle? You'll notice that the points A, B, and C are all on the circle, right? And they are all the same distance to that point M. That's what makes this a circle, is that all the points that are on that purple, that pink outline are all common point, a set of points that are all equidistant to a common point, to the same point, point M. Now, if all the points are equidistant to M, then that would mean that if I was to draw segments from all those points to M, all right, so if I was to draw segments from all those points to M, kind of like that right there, then what we would have is a bunch of things that we call the radii. And all of these segments are going to be equidistant. Okay, so all those segments right there are what we call radii for plural or radius for singular. And all radii in the same circle are congruent to each other. So if AM happens to be 10 inches, then that would also tell you that BM is 10 inches and CM is also 10 inches. So what we're going to take away from this is that if you start at the circle, right? So if you start on the circle and you end at the center, then your segment is what we call a radius. And all radii are congruent to each other. All right, so now I have a second circle. We got this circle here. This circle has a center at F, and we call this guy circle F. The circle above it, that first circle that we were working with, we call circle M. All right, so in circle F, you'll notice that there aren't that many radii. So the question then is why is WX not a radius? And it's once again because it doesn't start on, well, it actually starts on the circle. It starts at W, but then it ends at X, and X is not at the center, therefore WX is not a radius. The same thing can be stated for ZY. ZY is not a radius, and XY. XY is not a radius. But if you look closely, you'll notice that there is a segment on there, ZX, that does start and end on, that does start at the circle, but then it ends right there if you wanted to stop there at the center. So we could say that fx is a radius. We could also say that fz is a radius, but zx is not. Now, these other lines that you're looking at right here are what we call chords. Now, chords are segments that stop on the circle and start on the circle. So the reason why WX is called a chord is because W and X are both on the circle. That makes it a chord. ZY is a chord, and so is ZX as well as XY. So all of those are chords. Now you'll notice of the four chords drawn in this picture that one of them is actually a special chord. And that special chord is the chord ZX. Now if a chord happens to pass through the center of the circle, then we're going to call that chord a diameter. So in this problem, ZX is what we would call a diameter. Now what I'd like you guys to notice about this diameter is that it is actually made up of two radii. And this leads us to our final topic, and then that's that a diameter is equal to 2 of the r's. So let's go through it really quickly. What are the segments that we're looking at here? So in this first circle right here, can you identify any of the radii or the radiuses? And the first one is right here. This AM is a radius, as well as BM. BM is a radius, and CM. CM is also a radius. In the second circle, can you identify any other radius? And this is going to be one of them, and this is going to be our second one. So we do have those two radii right there. All right, can you identify any chords in any of these circles? And I'm going to go ahead and say, yeah, we can identify a couple of chords. All right, so this one right here is a special chord, but we also have this chord over here. This is a chord, and this is a chord, as well as that. That is also a chord. So all of those are chords. But in this circle, you also have this special chord, which is what we call a diameter. Okay. Now the diameter is equal to 2 radii. And this leads me to my last question. What if in circle F, by the way, we would call circle F like this. We would say circle F. There it is. There's the name for circle F. You could either write out the name circle or you can draw the picture. And this one right here, we're going to call this one circle M. Okay. All right, so back to my question. What if in this picture I knew that if I was to draw another segment right here and called it FR, if I knew that FR was 10, okay, if FR is 10, could I figure out how long ZX is? All right, could I figure out how long this whole piece right here, this whole diameter? So what I'm going to do is I'm going to turn that guy off, and we're going to try this one more time. We're going to say that what if I had this segment, RF. Now, since segment RF starts on the circle and ends at the center, we're going to call that a radius. And what if that was 10? Well, if that was 10, if RF is 10, you could now conclude that ZF is also 10. Because, as stated up here, radii in the same circle are all congruent to each other. Which means FX, that's right, FX is also 10. So if I know that RF is 10, I can conclude that both ZF and FX are also 10, which now leads me to believe that ZX is equal to 20, because I would add ZF plus FX. All right, Logan. If you have any questions, please hit me up on email. I'll get back to you as soon as I can. Hope you guys have a great day, and I'll talk to you later. Bye.